It's time to start solving some equations. In this video, we're going to look at linear equations, equations with rational expressions, and equations with absolute value expressions. Quick reminder of what it means to solve an equation. To solve an equation means to find all inputs for the variable or variables that make the equation a true statement. In this video, we're only going to be looking at equations in one variable. So we're just going to have to find the set of all possible inputs for that one variable that make the statement true. If there is no input that will make the statement true, we say that the equation has no solution. Let's start with the easiest type of equation, a linear equation in one variable. A linear equation is an equation where the variable you're solving for is raised to the first power. So in this example, 9x minus 8 equals 5x plus 4. The only instances of the variable are raised to the first power. So this is an example of a linear equation. The standard procedure for solving a linear equation in one variable is to isolate the variable you're solving for on one side. So we want to move all copies of the variable we're solving for to one side. We move everything that doesn't have that variable in it to the other side, and then often there's a multiplication or division step that we have to do in order to completely isolate the variable. There are a couple of really good first steps here. I generally try to get all copies of the variable to one side, so I'm going to subtract 5x from both sides. I don't want any copies of the variable on the right side, so I'm subtracting those away. And to balance that step out, I'm going to subtract those 5x's from the left side as well. On the left side, I combine like terms. 9x minus 5x is 4x. Bring down the constant term that we haven't used. On the right side, the 5x's cancel, which was kind of the point, to get rid of the variable term on the right side. And I just bring down the constant term, which is 4. Now that I've committed the variables to the left side, I want to move everything that doesn't contain that variable to the right side. So this minus 8's got to go. To move that, I can add 8. Negative 8 plus 8 will be 0. To balance that term out, I add 8 to the right side. On the left side, the 8's cancel, which was the point of the step. I get 4x. On the right side, 4 plus 8 is 12. And here's where you could use that division step to finish this off. But I also want you to remember that you don't really need algebra to do this. When you were in second grade and you were first learning multiplication, if your teacher wrote 4 times what equals 12 on the board, none of you would have said, well, don't we have to divide both sides by 4 to solve for the blank? Right? That's ridiculous. Or you were a very strange child if that was your first thought. You just guessed your way to the answer. You said, well, 4 times 3 is 12, and so the number in the box is 3. Remember that x is basically just a blank. We use letters in algebra instead of blanks because we could have multiple variables and we don't want to have to draw like 4 different shapes, like a rectangle and a hexagon and an octagon. That wouldn't work, so we use letters instead, but that x is just a blank. So x is equal to 3. Now, if it bothers you that I did it that way, you can just divide both sides by 4. That is the algebra step, but you don't need algebra to solve that. The nice thing about solving equations is that you can take the time to check to see if your answer is right. Remember what it means to solve an equation. It means that the input that you found will make the statement true. Is 9 times 3 minus 8 really equal to 5 times 3 plus 4? I put the question mark over the equal sign to indicate that I'm asking if this is true, not asserting that this is true. So let's see, on the left side we get 27 minus 8, and on the right side we get 15 plus 4. 27 minus 8 is 19, 15 plus 4 is 19. That is the solution. Now, to solve an equation means to find all possible inputs that make the equation true. You might remember from beginning algebra that there's a geometrical interpretation of this. We could think of the graph of the left side and the graph of the right side, and they are lines with 2 different slopes, and so they'll intersect at only one point. So this equation only has one solution. We verified that 3 is a solution, and therefore we've solved the equation. X equals 3 is the only solution to this equation. In general, a linear equation either has no solution, one solution, or infinitely many solutions. I want to do one more linear example, but I don't think you need to see more examples like this because they pretty much play out the same every single time. Also, the other types of equations we're going to talk about in this section will reduce to linear equations, so we'll get plenty of practice doing these. But I do want to do what's called a literal equation, which is an equation that has multiple symbols in it and usually represents some formula. In this example, we're asked to solve the equation s equals 1/2 gt squared plus v sub 0 t for v sub 0. This is an equation from physics. A lot of you will see it if you go on to calculus. This equation can be used to give you the height or displacement of an object that's been fired into the air from ground level. So S is the height or displacement, G is the acceleration due to gravity, T is the time, V sub 0 is the initial velocity. This equation gives us the relationship between all of those quantities. You can see that it's currently solved for the displacement. We've been asked to solve it for V sub 0, which is the initial velocity. Now I know this equation has a square in it, so it doesn't look like it's linear, but we're solving for V sub 0, and V sub 0, the variable we're solving for, is raised to the first power. So from the perspective of V sub 0, this is a linear equation. And what was our strategy? We want to isolate the V sub 0 on one side. I know we often like to have the variable we're solving for on the left side because there's some kind of comfort in that. But it's going to be more efficient to leave this V sub 0t on the right side and just move this term away from it. If I want to isolate the V sub 0, the first thing I have to do is move away this term that doesn't have any V sub 0s in it. So I'm going to subtract 1/2 gt squared from the right side, and to compensate I'm going to subtract 1/2 gt squared from the left side. So on the left side, those are not like terms, so the best I can do is just write them as a difference, s minus 1/2 gt squared, and on the right side I have V sub 0t. If at this point it annoys you to have the V sub 0t on the right side, you can just flip-flop the equation. But this doesn't bother me, so I'm just going to finish this off. To solve, I need to get the V sub 0 alone. Now in the previous example, you could just guess and check your way to the answer numerically. Here's where the algebra is useful. I want to divide both sides by t. I'm going to divide by t on the right side to make the t's cancel, and to compensate I'm going to divide the left side by t. You can do this by dividing the entire left side by t, or you can divide each term individually by t, which is what I would do here because it leads to a cancellation. So in the first term I get s over t. In the second term, I subtract the exponents on the t's, 2 minus 1 is 1, and this reduces to 1/2 gt. That's equal to V sub 0. Being able to rearrange an equation like this is sometimes necessary when you're trying to solve a word problem. Notice that the logic was exactly the same as the previous problem. In fact, from one perspective it was easier, because in this example we had copies of the variable we were solving for on both sides. We had to consolidate that first. Here, there was only one copy of the variable that we were solving for, so we just had to shift something away and then divide. It looks uglier, but from the perspective of steps, this one was actually easier. I think we're ready to move on to other types of equations. And again, if you don't feel confident with linear equations yet, the types of problems we'll be doing from here on out will often reduce to linear equations, so we'll get more practice with this procedure. The next few examples will have rational expressions in them. We're going to be solving equations with rational expressions. A rational expression is a special type of fraction, essentially. It's a fraction where the numerator and denominator are made up of polynomials. The general procedure for solving an equation with a rational expression in it is to multiply each term by the least common denominator. When you multiply everything by the least common denominator, that guarantees that all the denominators will cancel away, and you won't have to deal with the fraction look anymore. Next, you solve the resulting equation using whatever procedure works best for that type of equation that you get from the previous step. And then we have one extra thing we have to do. Because there's division by a variable expression in these types of equations, you have to make sure that you check for extraneous solutions. You're not allowed to divide by 0. And so if the candidate solution you come up with makes one of your denominators 0, then that's not actually a solution to the equation because you're not allowed to plug it in. It's not an allowable input. So you have to make sure that you're actually allowed to plug that number back into the equation. Your proposed solution doesn't make the equation true if you're not even allowed to plug it back in. So in this first example, we have 3 over x plus 5 equals negative 2 over x minus 5. And the general procedure is to multiply both sides by the least common denominator. So the least common denominator would be x plus 5 times x minus 5. So I'm just going to multiply both sides by x plus 5, x minus 5. The point behind this is that the denominators are guaranteed to cancel. X plus 5 and x plus 5 cancel on the left side. X minus 5 and x minus 5 cancel on the right side. And the remaining equation is 3 times the quantity x minus 5 equals negative 2 times the quantity x plus 5. Before I go on, a lot of you might have looked at that equation and said, well, why don't you just cross multiply? I want you to notice that the result of my step is exactly what you would get if you cross multiplied. 3 times x minus 5 and negative 2 times x plus 5. So it's okay to cross multiply here. I tend not to use cross multiplication when I demonstrate problems in class because that doesn't work on every problem. It only works when you have one rational expression set equal to another rational expression. If there was another term floating around in here, then the more general idea is the way to go. Now we haven't seen an equation like this in our class yet, but we can turn this into equations similar to what we've seen before by using the distributive property. If I distribute the 3 through the left side, 3x minus 15, and I distribute the negative 2 through the right side, negative 2x minus 10, now we have an equation similar to our first example where we've got copies of the variable on both sides. So we consolidate all of the variables to one side, would cancel the minus 2x by adding 2x, and then compensate by adding 2x to the left side. And because I know you guys have done equations like this before, I'm going to do two steps at once. Now that I've committed the variables to the left side, I know I want to move the constant terms to the other side, and so I'm going to add 15. That will get rid of the constant on the left, and then I'll have the variable isolated on one side. So on the left side, 3x plus 2x is 5x. The 15's cancel. On the right side, the x's cancel, and negative 10 plus 15 is equal to 5. Now again, you can use algebra to solve this, but that would really hurt my feelings. This says what times 5 equals 5. You don't have to exactly be a mental calculator to guess at that one. The solution is x equals 1. Now, let me go back to the original problem here, and let me get rid of this slash through the denominators. Is 1 an allowable input? Well, 1 plus 5 is 6. That's okay. It's okay to divide by 6. 1 minus 5 is negative 4. That's okay. So as long as we didn't make any silly mistakes, that should be our solution. If you really want to check, you can write the check off to the side. You can see that if you plug in 1, you make both sides the same. So this really is a solution. Let's look at an example where you're not allowed to cross multiply, at least not as your first step. Here we've got more than one term on the left side. This says 3 over x minus 1 minus 2 over x plus 1 equals 11 over x squared minus 1. If you collect these two terms together and write them as a single fraction, then yeah, cross multiplication is an option. In order to do that, though, you have to get a common denominator. And in order to get a common denominator, you have to find the least common denominator. Well, that's what we need to do in order to clear out the fractions anyway, so I wouldn't bother subtracting these first and then clearing the denominators. I would just clear them as soon as I knew what the least common denominator was. Some of you might be able to see what the least common denominator is right away. If you're not sure, you want to get all of your denominators completely factored first. So there's really nothing we can factor in the first or second rational expression, the ones on the left side. But on the right side, x squared minus 1 is one of those differences of squares. It factors to x plus 1, x minus 1. And when I get it factored like that, I see that every denominator either has a copy of x minus 1 or x plus 1. There are no other factors. And so if I multiply everything by x plus 1, x minus 1, it'll clear out all the denominators. In the first term, the x minus 1's cancel. So I get 3 times x plus 1. In the second term, the x plus 1's cancel. So we get minus 2 times x minus 1. And on the right side, all of the variable expressions cancel. We're just left with that numerator of 11. We've now reduced this to a linear equation, and it looks a little bit different than what we've done before. But we had a strategy that worked before. We distributed first. Let's do the same thing here. This is 3x plus 3 minus 2x plus 2. When you distribute here, you get a positive 2 equals 11. We've already got like terms on the left side, so I don't need to move anything. I just collect these as like terms. 3x minus 2x is 1x, which we usually just write as x. 3 plus 2 is 5. It's equal to 11. Again, you can use algebra to solve for x here by isolating. You can just realize that this says what plus 5 equals 11, and we get a proposed solution of x equals 6. Are we allowed to plug those back into the original equation? Let's see. 6 minus 1 is okay, 6 plus 1 is okay, 6 squared minus 1 is okay. None of those give us 0 in the denominator, so as long as we haven't made any silly mistakes, this is the only solution. Again, if you're not convinced, you can just check it. I've done it for you here so you can see that that really does make the two sides the same. If we were to collect those two fractions together, that really does give us 11 over 35, and so x equals 6 is the solution. Here's a very similar problem I'd like you to try. All I've done is change the numerator on the right side. Without going back to the previous problem, see if you can copy the steps and come up with the solution. Pause the video and give this one a shot. Okay, so we're going to multiply by the exact same thing we did last time. We're going to multiply everything by x plus 1, x minus 1. Let me write out the step. You don't actually have to show that this has been factored in order to get everything to cancel, but it makes it easier to see what the least common denominator is. So I multiply everything by that least common denominator, and I cancel where I can. And since we saw this before, I'm going to skip this step. This is just 3 times the quantity x plus. Same thing here, just be careful that you distribute the negative with it. This is negative 2 times x minus 1, that's negative 2x plus 2. And on the right side we have 6. We collect our like terms, it collects the exact same way as last time. This is x plus 5 equals 6. And then this is asking what plus 5 equals 6, or you could subtract 5 from both sides. And we get a solution of x equals 1, and that's our answer, right? Nope! No, that's not right. What have we forgotten to do? You got to check to make sure that 1 is an allowable input. If you go back to either the first rational expression or the third rational expression, you'll see that you're not allowed to actually plug 1 back into the equation. 3 over 1 minus 1 is 3 divided by 0. Division by 0 is undefined. 1 doesn't actually solve this equation because we're not even allowed to plug 1 in. Our only proposed solution didn't actually work. Because our only proposed solution didn't work, this equation has no solution. You should have guessed something was fishy when I asked you almost the exact same question. Only changing one number was a little bit weird, right? If I caught you with that, no, I don't apologize. I don't feel sorry for it at all. You should know to check. You check to make sure that you're allowed to plug those numbers in. If you fell for it, that's your fault. Let's look at a literal equation that has rational expressions in it. This is the most basic type. It says solve 1 over r equals 1 over r sub 1 plus 1 over r sub 2 plus 1 over r sub 3 for the variable r sub 2. So each of these r's actually represents a different variable. I know this looks funny, but this is a standard notation from electronics. This is an equation that deals with resistance. We're trying to solve an equation with rational expressions in it, and so we're going to multiply everything by the least common denominator. The least common denominator is the product of the 4 denominators because they're all distinct. There's no factoring we can do here. So we're going to multiply everything by r sub 1, r sub 2, and r sub 3. I'm going to rewrite this so you can see it a little bit better. So you can see that I've multiplied each term by the product of the 4 denominators using various levels of legibility. I know it's kind of hard to read some of those. In the first term, the r's will cancel and leave behind r sub 1, r sub 2, r sub 3. On the right side, the r sub 1's cancel in the first term, r sub 2, r sub 3. The r sub 2's cancel in the next term, r sub 1, r sub 3. And the r sub 3's cancel in the last term, r sub 1, r sub 2. This is a linear equation in terms of the variable that we're solving for. If we're solving for r sub 2, all of the r sub 2's are raised to the same power. So what was our standard strategy? We get all of the copies of the variable we're solving for on one side, and we move everything else to the other side. So I've got these two terms with r sub 2 on the right side. If I subtracted those over to the left side, then all of the r sub 2's would be on one side. So one way to approach this is to subtract r sub 2, r sub 3, and subtract r sub 1, r sub 2 from both sides. R sub 1, r sub 2, r sub 3, minus r sub 2, r sub 3, minus r sub 1, r sub 2 is equal to the only term that's left over on the right side, r sub 1, r sub 3, which has no r sub 2's in it. You have to move all of the r sub 2's to one side. You haven't solved an equation for the variable if you've got copies of the variable on both sides. So now we've run into another new situation. We've got copies of r sub 2 in each of these. These aren't like terms from the standard perspective, so how can we consolidate this? Well, it's the distributive property that comes into play. I'm going to factor the r sub 2 out of each term. So in the first term, I'm left with r sub 1, r sub 3. In the second term, we're left with r sub 3. And in the last term, we're left with r sub 1. That consolidates these all into one term. We actually use this property all the time. We just don't show the work anymore. In the first example, when we did 9x minus 5x, we just instinctively wrote 4x, but technically that's cheating. When you do 9x minus 5x, the order of operations says that we have to multiply here first. So how can we cheat and just subtract those coefficients? Well, it's the distributive property. Factoring out the x gives me a 9 minus 5. That's why we're allowed to subtract and we get 4x. We're doing the exact same thing here. It just looks messier because everything's a variable. We can't collect these together. Now we're going to divide both sides by this expression in the parentheses. And so r sub 2 is equal to r sub 1, r sub 3, divided by r sub 1, r sub 3 minus r sub 3 minus r sub 1. Again, the process for these literal equations is the same as what you do for the equations with the numbers in them. Just seems harder because of all of the symbols that you have to juggle around here. You can't really consolidate much together because you don't wind up with like terms like you do in the other examples. But the process is the same. We're going to move on to equations with absolute value expressions in them. Our general strategy will be to solve for the absolute value expression and then consider all possible cases. So in our first example here, I've already isolated the absolute value bars on the left side so that we can just talk about what I mean by consider cases. What we're thinking is that it's just the absolute value of something equals 7. Now, being an algebra person, I can't just leave that blank, so I'm going to put in a placeholder. I'm going to use u as a substitution. So what if this equation just said the absolute value of u equals 7? Well, we know that absolute value represents distance from 0. So this is really just asking what numbers are 7 units away from 0. Well, there are two numbers that are 7 units away from 0 on the number line. There's positive 7. There's negative 7. There are two cases that would make this equation true. If the thing inside the absolute value bars was equal to 7, or if the thing inside the absolute value bars was equal to negative 7. That's the same scenario we have in our actual problem. I'm just going to set the expression in the absolute value bars equal to 7 or negative 7. 3x plus 2 equals 7, or 3x plus 2 equals negative 7. And now we have two linear equations and we know how to solve these. The steps to solving these equations are going to be the same, so I'm going to do this in tandem. To isolate the variable term, I need to subtract 2. I'm going to do that in both equations. On the left, that gives us 3x equals 5, and on the right, that gives us 3x equals negative 9. Here's an example where maybe you don't feel as comfortable guessing, so the algebra comes to save you. The reason you have a harder time guessing is because the answer is a fraction, 5/3. On the right, I would do the same thing, although this one's easier to guess. Maybe you don't need to show that step here. This is negative 3. The correct word between them is or, because either x is equal to 5/3 or it's equal to negative 3. These two solutions cover the cases, and so we're done. Okay, so what did I mean when I said solve for the absolute value? Well, in some equation, the absolute value bars aren't by themselves, so our first job will be to get them by themselves. Again, I want you to think of it like there's a substitution there, like you're just trying to solve for this symbol. And so if that said something like 4k plus 1 equals 9, how would you get that k alone? Well, I think you'd all do the same thing. You'd subtract 1 and divide by 4. That's exactly what I'm going to do here. I'm going to subtract 1 from both sides. That's 4 times the absolute value of x minus 3 on the left side and 8 on the right side. And then I'm going to divide by 4. When I divide by 4 on this side, the 4's cancel. We just get the absolute value of x minus 3, and on the right side we get 2. And now you want to break this into cases. Pause the video and see if you can solve it from here. So either x minus 3 is equal to 2, or x minus 3 is equal to negative 2. Those are the two numbers that have an absolute value of 2. And so those are the two possible values of x minus 3. I don't think we need algebra for this. 5 minus 3 is 2, so one possible solution is x equals 5. Over here, 1 minus 3 is negative 2, so the other possible solution is x equals negative 1. You can go back and check those if you'd like. You'll see that they both work. This last example starts in the same way. Pause the video and see if you can isolate the absolute value bars, but then come back before you finish it off. Okay, so to isolate the absolute value expression, I'm going to subtract 3 from both sides. So we get 5 times the absolute value of 13x minus 7 equals negative 11. Then we divide both sides by 5. And we get the absolute value of 13x minus 7 equals negative 11/5. And then here's why I told you to check back in. Think about our substitution idea. If I change that to a u, this says the absolute value of our number has to be equal to negative 11/5. Don't split this into cases, because there is no case where this happens. The absolute value of an expression cannot be equal to a negative number. This can't happen. Absolute value always comes out non-negative. There is no value of x that will make this true. A common mistake is to split this into two cases like we have in the previous examples, and then just assume that those were right. If you do that, you'll get two solutions, but neither of them will actually make the equation true. This equation has no solution because it's impossible for the absolute value of an expression to come out to a negative number. That's why I said consider cases here and didn't say write two equations. If you've done this before, and I'm sure many of you have, if you've done this before, you know that the standard strategy is to separate this into two equations. But you can't always separate it into two equations because in some cases that doesn't happen. Like in this example, there's no way for this to happen. The absolute value of an expression can't be equal to negative 11/5. This equation won't have any solutions. We'll get more practice with these kinds of equations in the future. We'll be solving linear equations a lot as we solve more complicated equations. One of the steps is usually to reduce a more complicated equation into a bunch of linear equations, like we've been doing with the absolute value problems. We'll see some more complicated rational expression equations in the future as well. Make sure you get some practice on these. If you have any questions, give me an email. See me in an office hour.